Welcome back to the deep dive. You know that feeling. You're sitting in a planning meeting. Maybe the coffee's gone a little cold, the lights are buzzing, and someone asks you that inevitable question. So how long will this take?
The dreaded question.
Right. And you throw out a number, let's say, 4 days. And the second that number leaves your mouth, it undergoes this complete metaphysical transformation.
It really does.
In your head, it was an educated guess, a rough prediction based on, well, incomplete data. But in their head, it has instantly become a sacred, unshakable commitment.
Written in stone.
Exactly. The stack of sources you brought us today cuts right to the heart of this conflict. We are diving deep into the chasm that exists between the professional estimate and the business commitment.
And it is a chasm.
Our mission today is fundamental. We are going to stop viewing estimates as single, rigid points in time and start treating them as what they actually are.
Which is a probability distribution.
A probability distribution. We're going to equip you with the tools, including, and I love this, a surprising technique created for the U.S. Navy during the Cold War.
Get this, yeah.
To manage uncertainty, measure risk, and perhaps most crucially, manage expectations like a true professional.
This clarity is absolutely vital. I mean, if the people doing the work fail to define the variance, the range of possible outcomes, the business stakeholders will invariably define that variance for you.
And their definition of variance is?
Usually zero. They assume certainty. We have to fundamentally understand that the risk in any timeline, the difficulty in estimation, it's tied not just to the size of the work, but to the inherent structural complexity and the coupling of the system itself.
That's a powerful assertion. The time estimate isn't about speed, it's about navigating complexity.
It's all about complexity.
And to anchor this idea, let's start with an incredible historical anecdote that perfectly illustrates the pain of tightly coupled systems and, the astronomical risk that complexity injects into any timeline. Let's unpack this lesson in independent deployability. This is straight out of the year 1978. What was the setup?
So you have to picture the scene. 1978. You are working on an embedded system. A critical piece of technology. It's deployed widely in the field. The program itself was, well, by modern measures, tiny. 32 kilobytes of code.
Okay, 32K.
Written entirely in Z80 assembly language. Now, in that era, 32K wasn't just a single file on a hard drive. It was physically spread across 32 individual chips.
32.
Specifically, 1K by 8 EEPROM chips, and they were socketed onto 3 separate physical circuit boards.
So you've got 3 boards, 32 separate physical units holding the code. That sounds less like software and more like, I don't know, a piece of sculpture.
It was a logistical and operational catastrophe waiting to happen. It really was.
Yeah.
The company had hundreds of these devices deployed, often in very remote or difficult-to-access locations, like, telephone central offices all over the United States.
Right, so not exactly in the server room down the hall.
Not at all.
Yeah.
And if they found a simple bug, a single incorrect jump instruction, or if they needed to add a minor feature, what do you think that tiny code change required?
I think I know where this is going. Because it was all tightly coupled assembly, any change anywhere would shift the physical address space that followed it, right?
Precisely. You nailed it. That single line of added or removed code, it invalidated the content of virtually all 32 chips.
Oh, no!
The consequence, they had to send expensive field service technicians out to every single one of those hundreds of installations
Oh my God.
to physically pull out and replace all 32 chips.
Wow. So the coupling wasn't just logical, it was purely physical and address-based. The cost of deployment and, I imagine, breakage must have been astronomical.
It was completely unsustainable. And think about the physical risk alone. You've got these fragile chips. The pins would bend if you looked at them sideways.
I've bent so many of those pins.
Right. And the constant stress of pulling chips out could potentially damage the solder joints on the boards. Every single deployment was a high-risk, high-cost event. The manager, a guy named Ken, he realized they were paralyzed.
They couldn't improve the product.
They couldn't. They needed a way to change a small part of the code without replacing everything else. And this is where the developer discovered the essential professional lesson. Complexity makes estimation impossible, but independent deployability, that makes estimation feasible.
So what was the ingenious fix? How do you decouple 32 separate non-volatile memory chips holding assembly code in 1978? That sounds like a magic trick.
The concept was straightforward, but the implementation was absolutely brilliant. They had to transform each chip into an independent compilation unit, something that could be burned and deployed all by itself. So first, The developer analyzed the size of every single function in the application and wrote a custom program to fit those functions into the 1K chips, almost like solving a highly complex jigsaw puzzle.
A packing algorithm, basically.
A packing algorithm, exactly. And they intentionally left about 100 bytes of unused space on each chip for any future small patches.
Leaving buffer space, that's a lesson in itself right there.
It is. But the real question is, how do you handle the function calls? If a function on chip 5 needs to call a function on chip 12, it still needs to know its physical address. And if you update chip 12, that address is just going to shift again.
Right, you're back to square one.
This is the revolutionary part, the key architectural shift. They instituted a layer of indirection. At the beginning of each chip, they placed a table of pointers, like a directory, to all the functions contained on that specific chip.
Okay, so each chip has its own local map.
Exactly. Then, and this is critical, at boot up, all these little tables of pointers were moved into RAM.
Ah, so the volatile memory acts as the mediator, the central switchboard.
Yes, precisely. And the most important step, all the running code in the system was modified to call functions only through these RAM vectors and never directly to the physical EEPROM address.
Hold on, that's fascinating. I'm connecting the dots here. So if you change a function on chip 5, you only have to redeploy chip 5.
Correct.
And even though the physical address of the function on chip 5 has moved, the rest of the system doesn't care because everything else calls it indirectly through that known fixed RAM vector. The address in RAM never changes.
You got it. They had accidentally stumbled upon the fundamental principles of object-oriented design and polymorphic deployment.
That's incredible. The chips, essentially, they were behaving like objects with what are called V-tables.
Exactly, V-tables.
Wait, let's quickly clarify that jargon for the listener. What do you mean by a V-table?
Sure. Think of the V-table or virtual method table as that lookup directory we just described, that table of pointers. When you want to call a function, you don't call the function itself. You ask the directory, hey, where is the current version of the Frazzle function?
And the directory points you to the correct location.
It points you to the correct location. This indirection is the mechanism that allows a function to move or be replaced, to be polymorphically deployed, without requiring any other piece of the system to be recompiled or redeployed.
So this decoupling, it reduced the estimation risk from, what, we must plan for 3 months of field service risk and travel.
And broken chips.
To, we just need to estimate the time to burn and replace one single 1K chip. The complexity was managed structurally, which made the estimation problem smaller and, well, actually manageable.
It is the perfect starting point for this whole discussion.
Yeah.
Complexity and tight coupling are the enemy of reliable estimation because they create unknown unknowns. When you ask for an estimate, you are really asking for a prediction of the time required to navigate that level of uncertainty and coupling.
And if the coupling is high, the estimate is basically worthless.
It's unreliable. But if the coupling is low, the estimate becomes a practical professional planning tool.
This brings us directly to the core conflict identified in our source material. The profound and often painful difference between a commitment and an estimate. This misalignment of definitions is responsible for more professional friction, more arguments, more late nights than perhaps any other issue.
I think you're right. We must be crystal clear about these terms. So let's start with the business definition of a commitment.
Okay.
A commitment is fundamentally something you must achieve. If a project manager commits to a date, they are stating unequivocally that the deliverable will be ready by that specific time, period.
And the implicit cost of that certainty is steep. If you commit to a date and halfway through the project the unexpected happens, and it always does, right?
It always does.
Dependencies break, scope creep occurs, external forces intervene, you are still obligated to honor that deadline.
Absolutely. Honoring the commitment, if necessary, requires working 12-hour days, sacrificing weekends, canceling family vacations, and, burning the midnight oil. It implies a degree of certainty that often just does not exist in complex creative work like software development.
And the social contract is heavy. When you make a commitment, other people rely on that certainty to make their own plans. It could be marketing launches, sales campaigns, investor presentations.
The whole business plan might hinge on it.
Right.
Correct. And for that reason, missing a clear, explicit commitment in the professional world is viewed with extreme prejudice. Our sources are very, very blunt here.
How blunt?
Missing a commitment is viewed as an act of dishonesty, only slightly less onerous than an overt lie.
Wow.
So professionals only make commitments when they are absolutely certain of success.
Which brings us to the developer's reality. For the person actually doing the work, an estimate is defined very differently. It's a guess, a prediction.
Hmm.
No commitment is implied, no promises made. Developers often miss these estimates precisely because they don't know exactly how long something will take, especially at the beginning of the process when uncertainty is at its highest.
And this is the great insight the business needs to absorb. Missing an estimate is not dishonorable. It's not a moral failing. If Peter, the developer, says a task will take 3 days and it takes 4, he wasn't dishonest. He was simply wrong about a prediction concerning future uncertainty.
But the problem is that many software developers are viewed as terrible estimators.
Right, because they fundamentally misunderstand what an estimate should be, and they communicate it poorly.
Okay, so if the estimate is not a single hard number, what is it?
It is a probability distribution. This is the key insight that professionalizes the entire estimation process. When a developer gives a single number, they are engaging in a practice that statistical analysis shows is inherently flawed.
Why? Because of a cognitive error?
A pervasive one, yes.
Oh.
Are you familiar with optimism bias?
Absolutely. The tendency to believe that we're less likely to experience negative events than others.
Precisely. Humans are hardwired to be optimistic, especially when we're predicting our own abilities or, predicting a future where nothing goes wrong. When Peter says 3 days, he is mentally modeling the perfect path to completion,
The happy path.
the happy path.
Ah.
He is assuming the environment is static, the requirements won't change, his tools will work flawlessly. By communicating only that single optimistic number, he hides all the risk and basically forces his manager, Mike, to assume that the outcome is 100% certain at that point.
So if we can teach the business to understand the estimate as a distribution, a spectrum of possibilities rooted in statistics, we can shift the conversation.
Exactly.
You shift it from a moralistic argument over a broken promise to a rational discussion about risk management.
That's the goal.
Let's use the sources case study to bring this to life. This is the dialogue between Mike, the manager, and Peter, the developer, about the hypothetical frazzle task.
Right. So Mike asks Peter for an estimate. Peter, thinking he's being helpful, replies, 3 days.
And that single number is the flashpoint. Mike immediately starts planning based on 3 days. But he has no idea what Peter's internal confidence level is. Peter might feel 50% confident, or maybe 95%. Mike is going to be completely blindsided if the task takes 5 days.
Because Peter failed to communicate the necessary context, the uncertainty.
This is where a savvy manager should intervene, right? Instead of just accepting the single point, they need to ask for that context.
Exactly. The next question out of Mike's mouth should be, okay, 3 days. How likely is it that you'll actually be done in 3 days?
And Peter, being honest and professional, might reply, given the complexity of the database interaction, I'd say 50 or 60% confidence.
Now we have shifted the paradigm. Just with that one question, Mike now realizes there's a 40 to 50% chance they will be late.
So Peter has to proactively define the distribution's range now.
He must. He
And
should say,
yeah.
there's a very good chance it will take 4 days. It might even stretch to 5 or 6 days if we hit the integration issues I foresee.
He's now articulating the necessary and often unpopular right-hand tail of the distribution.
The pessimism, which is required for realistic planning.
And Peter needs to provide an anchor of certainty. He might say, look, I'm 95% certain I'll finish before 6 days have passed. But Mike, who's managing stakeholder expectations, he has to push further into the unknown. He needs to ask about the truly ugly possibilities.
The worst case scenario.
7 days, or even more.
And Peter's reply must capture the essence of Murphy's Law. He'd say, well, if everything goes wrong, and if the server goes down, if the legacy code base fights me at every turn, it could absolutely take 10 or even 11 days.
But he'd stress that's not likely.
Right. He stresses that this extreme outcome is highly unlikely, but its possibility must be acknowledged and included in the risk profile.
That moment where Peter states the possibility of 11 days, that is where the professional estimate is truly born.
It is.
We have visualized the uncertainty, just like in the sources figure 10 to 1. Peter's most likely outcome, his nominal estimate, is 3 days. That's the highest bar on the chart. But Mike, the manager, he now sees the tail of uncertainty stretching all the way out to 11 days.
And that long right-hand tail, that is the quantifiable risk Mike must now integrate into the project plan.
But the manager's instinct, of course, is still to eliminate that uncertainty. Mike tries to corner Peter. Peter, can you give me a hard date when you'll be done?
And Peter has to resist.
Yeah.
He has to say, no, Mike, I can't. I can only provide the probability distribution.
So Mike will try to solidify the date through negotiation. He'll say, so if 4 days is likely, can we just commit to 4 then?
And Peter must hold the line. No, because the data shows it could be 5 or 6.
And here comes the trap, the one hidden in plain sight that developers must learn to identify and deflect.
The loaded word, try.
Mike asks, Peter, can you try to make it no more than 6 days? Let's pause there and really scrutinize that word. Why is try such a dangerous contract in disguise? I mean, isn't trying a good thing?
Trying is effort, of course. But in this specific context, it's an implicit commitment. It's a verbal sleight of hand.
How so?
If Peter agrees to try, he is implicitly agreeing to expend unlimited resources to meet that target should difficulties arise. He is committing to the unpaid overtime, the canceled plans, the emotional toll, all this required to honor that date.
So if Peter agrees to try for 6 days and then chooses to go on his family vacation over working a weekend when the task runs into day 7.
Mike has the professional justification to accuse him of not trying hard enough.
I see.
Exactly. The commitment shifts from the external reality of the task, the complexity of the code, to the internal reality of Peter's personal sacrifice. Professionals have to maintain a boundary there.
So the rule is?
You only make commitments when you are certain of success. And you communicate estimates using clear, unambiguous probability distributions so that management understands the true cost of certainty.
This realization that a professional estimate is a measurable probability distribution, it didn't originate in modern startup, did it?
Not even close.
Our sources point us toward a formal technique developed specifically to deal with massive state-level uncertainty.
We're talking about the Program Evaluation and Review Technique, or PERT.
PERT.
It was invented way back in 1957 by Booz Allen Hamilton and the U.S. Navy to manage the Polaris submarine ballistic missile project.
Wow, okay, so this is serious stuff.
This was a project with immense complexity, pioneering technologies that had never been built before, and a timeline that absolutely could not fail due to the geopolitical stakes of the Cold War.
The Navy couldn't afford optimistic guessing from their engineers.
They needed a statistical method to predict timelines for components that, didn't exist yet.
So PERT is a system for that.
Precisely. PERT is a simple but profoundly effective scheme designed to convert a professional's subjective estimate, their informed guess, into a quantifiable probability distribution that managers can actually use for high-stakes planning.
The key innovation is moving from a single number to 3 numbers. It's called trivariate analysis. So instead of asking Peter for 1 number, Mike has to ask Peter for 3.
Right, and these estimates are specifically designed to bracket the entire spectrum of uncertainty.
Let's define these 3 anchors that structure the professional estimate. The first is the optimistic estimate. We call that O.
The optimistic estimate, O, is that perfect scenario we talked about. The sun is shining, the database is perfect.
The code compiles on the first attempt, and no one bothers you for 8 hours straight. A fantasy, basically.
It's the wildly optimistic guess. This number is designed to represent a ridiculously low probability of occurrence, like less than a 1% chance. It establishes the left boundary of our distribution.
So in Peter's example, for the frazzle task, his O was what?
His O was 1 day. It's physically possible, but statistically improbable.
Got it. Next, we need the nominal estimate, or N. This is the one Peter provided initially.
N is the estimate with the greatest chance of success. It's the peak of the probability curve, the highest bar on the chart. If Peter had to guess just 1 number, N would be it. Peter's N was 3 days.
Okay, and finally, the critical anchor for risk management, the pessimistic estimate, or P.
P has to be brutally honest. It needs to include everything going wrong that is reasonably within the bounds of a work project. The inevitable debugging struggles, the unexpected team meetings, the 2 days you waste solving a cryptic error in a third-party library.
It excludes literal acts of God, like a hurricane.
Right. It excludes hurricanes and stray black holes, but it includes every common failure mode. And just like O, this estimate must be a high number that has less than a 1% chance of occurrence.
So Peter's P was?
Peter's P was 12 days. That 12 defines the true breadth of the uncertainty.
So we have our 3 numbers, O1, N3, and P12. How do we take these 3 subjective guesses and mathematically generate a realistic planning tool? We need 2 key statistics, right? Expected duration and standard deviation.
Correct. The expected duration is represented by the Greek letter mu, and the standard deviation is sigma.
Let's start with the expected duration. This gives us the weighted average duration of the task. Now, the Navy realized they couldn't just average the 3 numbers, so not O plus n plus P3.
Right, because that would ignore the fact that the nominal estimate n is the most likely outcome. It deserves more weight.
So the PERT formula gives it more weight. It's no mu, O plus 4n plus P 6 segs.
Well, that's the one.
Wait, why? 4 times n. That's a huge weight. What does that mathematical adjustment tell us about human nature and the purpose of PERT?
That $4 is the statistical mechanism for correcting for our inherent human optimism bias.
Ah.
The Navy understood that people tend to underestimate the impact of complexity and overestimate the frequency of the best-case scenario. By weighting the nominal, most likely scenario 4 times more heavily than the extremes, the formula generates an average that is much more reflective of reality. It pulls the average towards the most likely outcome, but still accounts for the tails.
That's a beautiful way to enforce realism. Okay, so the formula is U$ plus 4n plus P 6UR. Let's run Peter's numbers. O is 1, n is 3, P is 12.
So we plug them in. $1 plus 4 times 3 plus 12, 66. That is $1 plus 12 plus 12, 66.
Which is 25 divided by 6.
Right. This calculates out to approximately 4.2 days.
Okay, 4.2 days. So Peter's nominal estimate was 3 days. The expected duration is 1.2 days longer than the single number he initially offered.
And that is the statistical evidence that the long right-hand tail of pessimism is warping the average duration.
It is the statistical correction for optimism. The gap between the optimistic scenario, O to n is 2 days, and the pessimistic scenario into P is 9 days. It's totally asymmetric.
And that long tail of risk pulls the average completion time further out, making 4.2 days the most honest weighted expectation.
Now for the critical measurement, the standard deviation. This is the measure of uncertainty, the quantifiable distance the results are likely to scatter from that 4.2-day mean.
Exactly. If the sigma is small, the estimate is highly certain. If it's large, the estimate is a major risk.
Conceptually, the standard deviation tells Mike how much he needs to buffer the expected duration. How widely do the results scatter?
And the formula simplifies this by using the distance between the two extreme scenarios, O and P. The wider that gap is between the best and worst case, the higher the uncertainty.
The formula for standard deviation is sigma, PO 66x. Let's calculate that scatter for the frazzle task.
Simple enough. We take 12 days, P minus 1 day, O, that gives us 11.
And we divide 11 by 6.
Which comes out to approximately 1.8 days.
So the standard deviation is 1.8 days. Mike now has 2 immensely useful numbers, an expected completion time of 4.2 days and a statistical risk measure of 1.8 days.
This is where management planning becomes scientific, not emotional. Mike understands that the task will likely be done within one standard deviation of the mean.
Which is 4.2 days plus 1.8 days, so 6 days.
Exactly. And crucially, if he needs 95% certainty, which is a common business requirement, he must buffer by 2 standard deviations or 3.6 days.
Which takes the timeline out to almost 8 days.
And this moves the conversation entirely away from finger-pointing and why were you late into informed risk tolerance. The question becomes, are we willing to accept the risk of a 6-day timeline, or do we need the certainty of an 8-day timeline? It's a business decision.
Now, in the real world, Peter is never just managing the frazzle task. He's managing a project, a sequence of tasks that must be completed one after the other.
Right.
This is where complexity truly explodes because the uncertainties do not simply add up, they compound in a much more punishing way.
Punishing is a good word for it. When you link tasks in sequence, the risk becomes multiplicative. The possibility of failure in any step delays the entire sequence.
So if we use Mike's planning scenario, he's managing 3 sequential tasks, alpha, beta, and gamma. We need to look at how these uncertainties stack up.
Let's do it.
Let's review the data we have. For task alpha, the expected duration, the new win, was 4.2 days with a standard deviation sigma of 1.8 days.
Right. Now for beta, the estimates were O1, N1.5, and P14.
Wow, a pessimistic of 14 for a nominal of 1.5? That's a scary task.
Yeah, it is. It signals a task that might be tiny, but it harbors huge potential pitfalls, a hidden dragon.
Right.
So despite the tiny nominal estimate, that brutally high P gives beta a NAVI of 325 days and a massive sigma of 2.22 days.
Okay, so high uncertainty on that one. And for gamma, we have O3, NE 6.25, and P11.
So the muter for gamma is 6.5 days, and its sigma is a relatively tight 1.3 days.
Okay, so to find the total expected duration for the sequence, the tower for the whole sequence, the calculation is mercifully simple.
Thank goodness, we just add the individual expected durations.
So 4.2 for alpha.
That's a great question, and it speaks to the core of statistical variance. If we simply added the standard deviations, we would be assuming that the errors in the tasks are perfectly correlated, meaning that if alpha runs late by 1 day, beta and gamma are guaranteed to run late by their maximum amount as well. But that's usually not the case. The delays and the early completions, they're generally independent events.
So we can't add standard deviations directly.
No, you can't. You have to add the variances. And variance is simply the standard deviation squared, sigma through to 2.
Okay.
The rule is that the variance of the sum of independent random variables is the sum of their variances. So the calculation for the sequence standard deviation is the square root of the sum of the squares of the individual standard deviations.
Let's walk through that slowly. We take our standard deviations, 1.8, 2.2, and 1.3.
Step 1, square them to get the variances. $1.822 is $3.24. $2 is $4.2 and $1.322 is $1.69.
Step 2, sum those variances. $3.24 plus $4.84 plus $1.69. That totals 9.77.
And step 3, take the square root of that total variance, 9.77, to get the final sequence standard deviation. And that comes out to approximately 3.13 days.
So Mike now knows the sequence has an expected duration of 14 days with an uncertainty of 3.13 days.
Which means
This means the project could easily take 17 days. That's 14 plus 3.13. Or if Mike needs that 95% confidence level, it could take up to 20 days, 2 standard deviations.
and that 20-day mark is the only honest commitment Mike can make to his stakeholders.
This is the brutal realism of compounding uncertainty. The combined uncertainty is always greater than the sum of the optimisms.
Every single time a human being estimates a complex series of tasks, they fail to account for the statistical compounding. PERT forces that realism right onto the plan.
This feeds directly into the law of large numbers. You mentioned that breaking down large tasks helps manage error. Let's dedicate some time to explaining why that works and why it's so critical to the estimation process.
Absolutely.
Yeah.
The law of large numbers dictates that the larger your sample size, the closer your average result will be to the true expected value. So when we estimate a single massive task, say, implement the new billing system, we're generating just one data point.
And if that one estimate is wrong, say 3 weeks late, there's no way to compensate. The whole project is just late.
Exactly. But if we break that giant task into, say, 50 small, independent tasks,
Now we have 50 small data points.
and the implication of the law is that the sum of the estimates of those 50 small tasks will be far more accurate than that single large estimate for the composite task,
Hey.
because the errors tend to integrate out.
Explain that phrase, errors integrate out.
Think about it like flipping a coin 100 times. You expect 50 heads and 50 tails. You might get 53 heads, but you probably won't get 90 heads. The more times you flip, the closer your result gets to the true 50-50 probability. In task estimation, Peter might underestimate task 1, that's a negative error,
Oh.
and he might overestimate task 2, a positive error. If the tasks are small and independent, those positive and negative errors tend to cancel each other out over the course of the 50 tasks.
I see. The large single estimate is dominated entirely by that catastrophic failure mode, that one big 12-day pessimistic tail. But when you break it down, a lot of small pessimistic tails can get canceled out by a lot of small optimistic heads.
Precisely. And there's another benefit. Small tasks force you to confront the implementation details sooner. You uncover those surprises, the unknown unknowns, that often hide inside a massive monolithic estimate.
This is why modern Agile practices emphasize small, independently deliverable increments.
It's not just about delivering value sooner, though that's important. It's a statistical technique to improve estimation stability.
So by breaking things down, you achieve 2 things. You force yourself to uncover hidden complexity, and you leverage the law of large numbers to ensure the sum of your estimates is statistically more reliable than the guess for the whole.
That's it.
So far, we focused on the math of converting estimates into distributions. But the math is, well, it's useless unless the initial guesses, the O, N, and P, are accurate.
Garbage in, garbage out.
Exactly. And the most critical resource for generating those figures is the collective intelligence of the team that's actually doing the work.
Right. Relying on a single individual, even an expert, is inherently risky because of that optimism bias we keep talking about.
We need techniques to efficiently gather estimates and achieve consensus from a group without bias creeping in or, one dominant voice skewing the results.
Absolutely. The sources highlight several key methods that are used to generate that high-quality nominal N estimate and also to establish realistic bounds for O and P.
Let's start with Wideband Delphi. This is a methodology that predates modern Agile, popularized by Barry Boehm back in the 1970s.
Wideband Delphi is a consensus-building strategy based on iteration. A team discusses a task requirements and complexities. Then, each member privately submits an estimate.
Privately is the key word there.
anonymously even. The estimates are collected and reviewed by the group. The group then discusses the divergences. Why did one person estimate 5 days and another estimated 10? The discussion focuses on uncovering risks and assumptions that others might have missed.
Then they reestimate.
They reestimate, and the process repeats until the estimates converge into a tight, agreed-upon range.
The power here is the iterative discussion and the anonymity, which prevents social pressure from influencing the numbers. So how does this feed into PERT?
It's excellent for refining that single nominal estimate, n. Once consensus is reached, that final agreed-upon number is your n.
And for O and P?
To apply PERT's trivariate analysis, the team can simply take the most extreme numbers submitted throughout the entire process. The lowest estimate ever given becomes O, and the highest estimate ever given becomes P. This ensures the range of uncertainty is bracketed by the collective wisdom and pessimism in the room.
Next, we have flying fingers. This sounds like a much lower tech, lower overhead way to achieve the same goal.
It is. It's great for rapid small group sizing. After the task is discussed, every participant puts their hands below the table and, on a count of 3, raises 0 to 5 fingers simultaneously.
And the fingers represent the estimate. Maybe 1 finger is a day or something like that.
Right, you agree on a scale. And why is the simultaneous reveal so crucial here?
It's to mitigate anchoring bias. If one person estimates aloud first, everyone else's number tends to gravitate toward that initial anchor, even if they privately disagree.
You're exactly right. By revealing estimates simultaneously, everyone commits to their independent assessment first. If there's a difference, say someone shows 1 finger and someone else shows 5 fingers, the team stops, discusses the discrepancy, and repeats the process until they achieve consensus.
And the discussion centers only on the extremes, which makes it highly efficient.
Very efficient.
This concept of simultaneous reveal is perfected in one of the most popular modern techniques, planning poker.
Right. Planning poker, which was introduced by James Grinning in the early 2000s, takes the flying fingers principle and formalizes it with cards. It often uses the Fibonacci series 0, 1, 2, 3, 5, 8, 13, 21, and so on.
Plus maybe cards for infinity if it's unsolvable or a question mark if it needs more info.
Yep.
Why the Fibonacci series? Why not just linear numbers like 1, 2, 3, 4, 5?
The Fibonacci sequence is used because it reflects the increasing uncertainty that comes with larger estimates. The difference between a 1 and a 2 is small and meaningful, but the difference between a 21 and a 22 is basically meaningless noise.
You're just saying it's huge at that point.
Exactly. If a task is so large it requires a 21 or a 34, the difference between them is irrelevant. You're simply stating it is massively uncertain. The scale itself forces the team to acknowledge that estimation reliability decreases non-linearly as the size increases.
And the process is similar. Moderator explains the task, everyone picks a card and holds it face down, and they reveal simultaneously.
Right. Disagreement is the goal. If the estimates scatter, the people with the highest and lowest cards must explain their reasoning. The person with the high card might highlight a hidden dependency the team forgot about.
And the person with the low card might have a simple library solution in mind.
Exactly. This exchange of knowledge often reveals risks or efficiencies the team didn't know existed. They play subsequent rounds until they reach a consensus number for n.
Finally, we have affinity estimation. This seems tailored for situations where you have a huge backlog of items or are trying to size tasks relative to customer value.
It is. Affinity estimation, popularized by Lowell Lindstrom, is unique because it removes the numbers entirely at the start. Tasks are written on cards and the team stands around a table or a wall, often including business stakeholders.
And the physical silent sorting process is key.
It is entirely silent, at least initially. The team's job is to sort the tasks relative to one another. Smaller tasks move to the left, larger tasks move to the right. Any team member can move any card, which is critical.
So if I see you moving a card I think is small to the right, I can silently just move it back to the left.
Right. And this continues until a consensus is reached on the relative ordering of complexity. When the cards stop moving, you've got consensus.
Only then do you bring in the numbers.
Only once the ordering is stable does the team introduce the numerical buckets, often those same Fibonacci sizes like 1, 2, 3, 5, 8. They group the cards into these buckets. Affinity estimation is exceptional for speed, for leveraging visual consensus, and for ensuring a shared understanding across technical and business roles about what small really means compared to huge.
So all these group techniques, Delphi, flying fingers, planning poker, and affinity estimation, they are tools professionals use not just to guess, but to generate a high-quality, consensus-backed, nominal estimate N.
and to identify the bounds for the optimistic O and pessimistic P values. And that creates the robust foundation you need for a meaningful PERT analysis.
If we synthesize everything we've covered, the key professional mandate seems really clear.
It is. Professional software developers provide practical estimates that business stakeholders can use for planning. But they absolutely must not and will not make commitments that they cannot keep, especially in the face of uncertainty.
They preserve their professional integrity by communicating estimates not as single, rigid promises, but as what we've been saying all along.
Probabilistic statements.
Probabilistic statements. These statements describe both the expected completion time and the likelihood of variance or uncertainty. This just shifts the whole dynamic.
It does. The methods we've discussed, trivariate analysis, PERT, and these group consensus techniques, they are not optional academic flourishes. They are practical tools required to convert a subjective, optimism-biased guess into a meaningful, objective probability distribution.
They force realism onto the planning process.
And they acknowledge that the long, dark tail of possible delays must be managed actively, not ignored.
It all comes back to defining expectations, honestly. If you're asking someone for an estimate, you now know that a single number, like 3 days, is incomplete. It's scientifically unsound, and it's professionally dangerous because it hides the quantifiable risk inherent in the work.
And that standard deviation, that sigma, that is the true professional metric.
Yeah.
If the work is highly uncertain, say, dealing with the complexity of that 1978 Z80 code, the estimate needs to communicate a high standard deviation.
And if the work is routine and well understood, the standard deviation will be small.
Exactly. That quantifiable measure of scatter is the very definition of a professional, educated guess.
So the next time you encounter a deadline, or the next time you are asked to provide a timeline for a complex coupled task, don't just say 4 days. Ask yourself the key question, the ultimate test. Can I calculate the expected duration and the standard deviation of that work? Because if you can communicate those two statistical realities to your stakeholders, you are no longer making a risky, optimistic commitment. You are providing a robust, professional, educated guess that allows for intelligent risk management. That is the true art of the estimate.
And if you're feeling ambitious, next time you are planning a series of complex tasks, actually calculate the sum of the variances. You might be surprised, shocked, even at how quickly the uncertainty grows. And that realization, that might be the thing that forces you to break those large tasks down into smaller, more manageable units to really harness the law of large numbers.
A sobering thought to end on.
Go deep on that realization. You will never estimate the same way again.